All right, welcome back to the organic chemistry alcohols chapter. In this section, we're looking at the Grignard reagent, and yeah, I think we should just hop right into it. The slide does look a little intimidating at first. This is probably the first time you're dissecting a carbon metal bond, right? So, just simply, the Grignard reagent is an organomagnesium, meaning um, it's an organic molecule with a magnesium in it. Quite simple. But it's important to know that this is a delivery agent. Now, we did see delivery agents with lithium aluminum hydride and sodium borohydride, but this one here, it doesn't deliver hydrogens. It is going to deliver alkyl groups, right? That's what that R is down here in this thing here, and it's going to reduce ketones by -1, and we're only going to see in this chapter it be used with ketones. Um, so I just want to dissect what the Grignard reagent is and what it looks like. I decided instead of drawing it out, it was a little bit easier to just put it on a slide. And also, it was made by this guy here, Victor Grignard. He won a Nobel Prize for it, so quite an awesome dude. But here we can see the general formula for a Grignard reagent is an R group bound to a magnesium bound to a halogen. Now, ignore these ionic charges that I gave it. We'll get back to that in a second. But let's look at the electronegativities of these atoms here. So we know that to be ionic, you need to be 1.7 Paulings in electronegativity difference, right? Anything below that's covalent, right? But you can have a lot of ionic character while still having a covalent bond. You just have to get really close to ionic. And that's what the Grignard reagent does. So if we look at the electronegativity of carbon, it's about 2.55. Magnesium is about 1.31 Paulings. So that gives us a total, and I put delta, kind of inaccurate, but the difference in electronegativities is 1.24. So we're about 0.5, 0.4 from being an ionic bond. So it does have some ionic bond character. But what's different here is that we have a halogen on the outside. And what that halogen does is it's going to induct positive charge from that magnesium, making it less electronegative, you could say. And that's going to bring this carbon magnesium bond basically to ionic. It is just under 1.7, probably around 1.5 to 1.6. So yeah, that bond is very polarized with your R group having a negative charge, which means it's going to act as a nucleophile. We'll see why that's important when we go through the mechanism of Grignard's. And it's going to give magnesium basically a positive charge. It's not ionic, but it's very close, and therefore we can treat it as ionic. So when you see a Grignard reagent and you see the covalent bonds, give that R group a negative charge on that first carbon, give that magnesium a positive charge. It'll make life a lot easier. Now let's get into the mechanism of how this works. Okay, so first of all, how do we prepare the Grignard reagent? Well, you need an alkyl halide, and for this we'll use bromopropanol, or bromopropane. Oh my goodness, I had a total brain fart there. So how you prepare a Grignard reagent is you just give it magnesium in a nonpolar solvent, so we'll use tetrahydrofuran for this, right? And we know that this is a group 2 metal, so that means that it's going to have 2 electrons on its in its valence shells, right, that it can use. Magnesium doesn't mind losing these electrons, right? Most of the chemistry we've seen, they like to gain electrons. This one, not so much. It's okay. If it loses 2, it can get that full subshell in the lower orbitals that it will utilize. So this is going to go through what's called a radical mechanism. Now, you've seen radicals, hopefully. That's why we cover it before alcohols, because you need to know the radical mechanisms before you get to this chapter so you understand the Grignard reagents. We're going to see a homolytic bond cleavage here. This carbon-bromine bond is going to break homolytically, but we're going to have coupling of the magnesium and the bromine. So what you're left with is, and I'll just draw the electrons in the same color. You have an electron on your propane, or any R group, for example, and then your magnesium, bromine, so we'll just draw this in green. It's going to form a bond, and you'll see that magnesium will still have that second electron it can use, and that's key to this reaction here. So they're going to couple like this, and we're going to get our final little product here, which is our Grignard reagent. So magnesium, bromine. Okay, so that's how we prepare the Grignard reagent. Quite simple, just a simple little radical mechanism where magnesium kind of butts its way in between that bond. That's how I like to see it. So if you're not asked the mechanism, and you just say, okay, we want to prepare the Grignard reagent, where is it most likely to do this? Show the mechanism, or don't show the mechanism, I guess. That it basically just butts in between. So quite simple. Now let's look at the reaction of our Grignard reagent. Again, it's going to be a delivery agent, so I'm going to use a ketone here to keep things nice and nifty. So I'll draw the ketone in a different color. So if we have our ketone here, it kind of looks like a Nerf ketone. That's kind of cool. If we have, and let's say we want to add a methyl group in this position here. So methyl group right here on that carbon. Well, we want to use a methyl Grignard. Quite simple, right? Whatever you want to add, make that your Grignard. So our reagent would be CH3, Mg, and then you can use any halogen, but for this case we'll use bromine. And then you follow this up in a separate step with acid. Quite simple. And basically it's going to do almost the exact same as our, what's it called, our hydrides, right? The lithium aluminum hydride and the boron hydride. So all that happens here is, remember, we can treat this like it's ionic, so carbon has a negative charge, and we know carbon with a negative charge, that we've never seen stuff like that before. So what's going to happen is it's going to come in, it's going to attack, and it's going to dump electrons. So, and then this gets kicked off, right? This group kicked off. So, and what that leaves us with is our methyl group. So I'll just draw this CH3, and then we have a negative charge, and then we simply protonate it with some species. We'll just use a generic acid, so we'll just say H plus comes in like that, and you then have your methyl Grignard. Look at that, guys. So you made it into an alcohol. It's a way to prepare alcohol, but if you want to add a group to it, you can. And it converts like if you had a primary, it will make it secondary. If you have a secondary, it makes it tertiary. Yeah, so that's how that works. That's the mechanism. Quite simple. Okay, so one more thing that the book covers that I think is important. If you remember what an ester is, you'll know that an ester is a carbonyl carbon, and then we add ester group, oxygen just in there, so I'll just draw it like this. All right, so how do these react with Grignards? These react a little differently. You're going to get two additions of a Grignard. So if we, again, let's just add methyl groups. So we're going to use a methyl Grignard. Magnesium, Br. Okay, and this has a negative charge, basically. This has a positive charge. So what happens here, the negative charge will attack like so. And it's going to dump electrons off here. So let's draw it like this, shall we? So we have our methyl group attached, and we have oxygen with a negative charge. Now, we could simply protonate it, but that's actually not what happens here. Something silly. You've probably never seen this before. If you did, that's awesome. If not, no worries. So that negative charge is called arrow pushing. It's going to arrow push out that ester group. Now, it's not an amazing leaving group, but it is a leaving group. And ultimately, that is what will occur here to give you this. Given enough time, the reaction will favor this. Because You think it could get protonated, sure, but it could also go reverse and then do this, and that is what happens given enough time. So we're back to just a ketone. So we had an ester, now we have a ketone. And we just do the same thing as we saw. So I won't bore you with the steps here. Not lithium aluminum hydride, a methyl Grignard. Jeez. MgBr, for example. You could use iodide here, but bromine's a good choice. And then, of course, here we need the acid workup. Note that we did not need an acid workup step here because that negative charge did not need to be neutralized. Here it does. So when you do this reaction, again, you attach your methyl group and you do an acid workup step, and you get a tertiary alcohol. So quite simple. Okay, one last little trick for you here. Let's see if I can get you. I want to do a Grignard with a carboxylic acid. Can you do it? I want you to think long and hard about this. Don't skip ahead, and if you really have to, that's okay. But really give it a good shot. Do you think a Grignard reaction would happen here? I'll draw this out while you think. Alright, if you still need time, pause the video. If not, you are good to go, and we will discuss this. So, step 1 and 2. Problem is, you're never going to get to step 2. So let's just cross that out. If you have a carboxylic acid, remember what this species is here, the Grignard reagent. This basically has a negative charge, and we know carbon with a negative charge is going to be so sad with that negative charge compared to either nitrogen or oxygen or a halogen given, that it's going to just attach, right? The pKa of CH4 is about in the 50s. So if we have a pKa of a methyl group in the 50s, what do you think that says about its conjugate base? Well, it's extremely strong, so that means that it's going to, instead of attack this slightly positive center here, it's going to first deprotonate this to give us a carboxylate ion, which looks something like this. So that's why carboxylic acids are not good for Grignards. They just deprotonate that alcohol group there, and yeah, you're left with carboxylate, which is this ion here, carboxylate. So a little trick question that a professor might put on an exam asking you to predict the products. This is your product. You will never get to this acid workup step right here. It's quite sad. Thank you guys for watching. I hope you enjoyed that episode. Grignard reagents are one of my most favorite reagents in the entire organic chemistry world. They're awesome. You're going to see a lot more reactions using them in the future. Same with your hydride reagents. So I hope you guys enjoyed. And be sure to subscribe, comment if you have any questions. I would love to answer your questions. And have a wonderful day.